Okay, a Saturday morning it isn't, but it's our Friday. And we're doing our tutorial. And this is our Math 20. And that was Joni Mitchell. That's a new album courtesy of Starbucks and their effort to do something besides coffee. And that was the Big Yellow Taxi, which is one of the few songs in there that was a little bit upbeat, and that's why I selected that. We were just going through a mix of our own as Chris was trying different songs. And so we have two different things I want to do today. One is to talk about a question that Tabitha has asked about, which is a problem dealing with currency. And that is a classic algebra problem that you've asked about, and we will get to that. Before I do that one, I had told you that I'd like to spend some time on 5.2 and 5.3. So I would like you to open your books to 5.2 and 5.3. And in 5.2, as I shared with you yesterday, a lot of what we're doing is just reducing fractions. And so as I come to the document cam and try to get something reasonably flat here, we have a problem like, for example, number 38. Don't go there yet, Chris. I was going to try to block that off because there we go. Now we can do it. Number 38. And I don't know if I can get that any lighter than it is. That's puzzling to me. Let me try. Just come off there for a moment. I'm going to see if I can do a white balance in this. It's just one of those days with technology. Let's try it again. Well, that'll have to do. I'm going to go to the board with that, Chris, as 168 over 105. And as we do this, we had this in a Math 10. And the version of this in Math 10 that I want you to do is called prime factoring, where you would write each of these as a product of primes, meaning the numerator and the denominator, and I'm on page 500, not 500, 315. 314, so 314. Does that remind you of anything? The page number. Does it remind you of anything? It should. Put a decimal point in it, and you have the first three digits of pi. How could you not notice that? Okay. Too early in the morning. At 10 o'clock, Robert? Come on, give me a break. So what are my primes? I'm going to list them, just as a reminder.
2, 3, 7.
2, how about the 5? 7, 11, 13, 17, 19, and then we stop. We can keep going forever, but that'll do it for the moment. So at this point, I'd like to write each of these as a product of primes, and so I would take, this is just a review, we take a 2 into here, and that's going to go in 84 with short division. We do a 2 again, short division again at 42, a 2 again, and that becomes 21. I cannot do the 2 at that point. I go to the 3, I get the 7, and when I get to the 1, I know I'm done. The most common mistake, once you've done the prime factoring, is to put this in the wrong place up here. So once you get that 168, I would really encourage you to write that in up here. Now, I'm going to do the same thing for the denominator. That was 105. And so I note that 105 cannot be divisible by 2, so I'm done with that. Then I go to what?
3.
The 3 and the short division. And I'm not taking time to do that on the board, but it's something that we talked about in the Math 10. I can't do 3 again. Divisibility rule, add the digits. You get 8. 3 will not go into that evenly. You go to 5. You get the 7, and the 1. Now what we did in the Math 10, which is our intro course, is we left those in that form. And we canceled them out. Now before I cancel out the common prime factors, I'm going to rewrite it with exponents and make a segue into the algebra. So this is 2 to the third, 3 to the first, 7 to the first. It's over 3 to the first, 5 to the first. I was going to make that in a little different order. I think I'll just stay with the order I have here. Now, in canceling out the common factors, we end up with a 3 and a 3 and a 7 and a 7, correct? And we think in terms of replacing those with 1s. So I have 2 to the third, which is an 8, over a 5. So we know that this is going to come out as 2 to the third over 5 to the first, which you would write as 8 over 5, and then you have a choice of doing what? A mixed number if you wish, not obligated. Now, if I look at it in this way, with the 3 to the first over 3 to the first is 7 to the first over 7 to the first, I note that I have a common base and exponent. And I'm going to, okay, now I've got to stop and think what we've done or haven't done at this point. We've done subtraction of exponents, correct? So I could say that I have 2 to the third, and I should have put in terms of arithmetic, the times symbols there for the moment, times 3 to the first minus 1. Then I have a 7 to the 1 minus 1, and that's over 5 to the first by subtracting exponents. So 3 to the 0, 1. 7 to the 0, 1, and I get my 2 to the third over 5 to the first. We've done that before. Just subtract the exponents. If I change the problem to where there are variables involved, and this is called a rational expression because I have a fraction with variables in the numerators and denominators. So as I come back center for a moment, Chris, and just slide this up a little bit without knocking things off, what I want to look at is something like the 50th problem, and let me get that in clearer focus. Okay, let's try that. Number 50. So this is the 50th problem, number 50. And could you leave that on the screen, the document cam for a moment so I can see the problem, and then we'll write it on the board, and then we can come back to the board. So I have 10m to the 7th n over 30m to the 9th n to the 4th and the letter p. Now I can go to the board. So this is my problem. Now I'm not going to expect you to write the 10 and the 30 with primes. I hope you realize that in terms of what we're doing there, these will cancel, giving you 1/3. But what I do want you to then realize is that there is a missing exponent, a 1 here and a 1 here. Those are the missing exponents. And the missing exponents are going to allow me to subtract exponents because I have here m to the 7th and the m to the 9th. Now, we've done negative exponents before. We did that in Math 10 where we were talking about expanded notation with a decimal. So I'm going to look at this as m to the 7 minus 9. Subtract the exponents because I'm dividing. And then I have an n to the 1 minus 4. I still had the 1 up here. Now, whether you put the 1 here or not's up to you. I have the 3. I've taken care of the m and the n, and I have p to the first. Now, that's just using the rule that says if you have a to the m over a to the n, that is a to the m minus n. And notice when we do that, this becomes m to the minus 2, n to the minus 3 over 3p. I'm going to ask you, what did we agree that 10 to the minus 3 meant, going back a semester? It meant what? How did I define 10 to the minus 3? Well, you're thinking in terms of going to a decimal. I want the definition of 10 to the minus 3. What I was searching for is what I'm not hearing. It is 1 over 10 to the third. So whenever you have a 10 to a negative exponent, it means you in essence have 1 over that base to the positive exponent. That's all we mean by 10 to the minus 3. There's no magic to that. There is no particular reason in making that definition until you hit a problem like this. Because I have n to the minus 3 here. If I had looked up here, n to the first over n to the fourth, I have n once here and 4 times here. I can cancel out one of them. I have 3 left in the denominator. So that would have been the same as, so I'm going to look at it in a different way. I would have had the 1. That would have been okay. I would have had the 3 down here, and I'm arguing that this 1n and these 4 n's multiplied together would have just given you 3 of them in the denominator, hence n to the third. Same argument. This m to the 7th says you have m times m times m times m 7 times. Here you have it 9 times. So how many are left in the denominator? 2. M squared. That takes care of these and these 2 factors, and I'm left with p down here. So I have the reciprocal, if you will, of 3m squared n cubed p to the first. Well, that's exactly what this says. I'm going to take this as m to the minus 2 times n to the minus 3 times 1 over 3p. Well, that's 1 over m squared by definition. This is 1 over n cubed, and I have it multiplied by 1 over 3p, and don't I get that? Well, the usual demand at this point to avoid the negative exponents is to write your answer so all the exponents are positive. That's the usual expectation. So if I look at what's been done in the solution, as I come back center, this is precisely what's been done by the author in the text as we go back to the document camp. Now that's a little bit hard to see, so let's see if I can bring that in a little bit tighter, a little better focus. That light blue is not so easy to see, but you can see the 3m squared n cubed p. And that's exactly what I have on the board. But what I want you to understand is that as I go to this board presentation here, and let's slide over just a little bit, Chris. Thank you. This rule works for any m and n that are whole numbers. That means I can do this immediately and get to here with one rule. And then I just need to understand what you let go of out of Math 10 a lot faster than I thought you would. 10 to the minus 3 means 1 over 10 to the third. No, but it has nothing to do with the number line at this point. Okay, but it's simply a matter of we understand that when I write this, I mean this. And that's no different than when I look at a flower and you've never seen the flower before and I say, that is a rose. Why? There's no reason at the moment. That's a commonly agreed term for that flower. Okay? You just accept it. And that's what you have to do here. That when this is written, 10 to the minus 3, you understand that is the same as 1 over 10 cubed. And that holds with any base. So again, n to the minus 3 means 1 over n cubed. And that's what I did here, is simply rewriting it. Thank you, Chris. Now, if you get that, every problem in this set, same way. If you want to go ahead and make sure that when you have an m to the 7th over an m to the 9th, you're going to have an m squared, that'll work. But I'm wanting from you, based on your background, just a little bit more than that. And now, Sandra, your question.
I understand the and thing, I think. I'm pretty sure I do. But the only thing I kind of am confused about is it looks like you're dividing 10 into itself, it goes into it once.
Whoa, whoa, whoa. 10 into itself. Okay, up here you're talking about.
Right.
I did cancel that way. 10 into 10 went once. 10 into 30 went 3 times.
Right. But I thought a normal division problem that was set up like that, you'd go from you divide the denominator into the numerator.
Okay, the question is, in a regular, normal division problem, and I had 10 over 30, you didn't want to reduce it, you'd say, okay, let's divide 30 into 10, and let's get a decimal, which would be 0.333333. In these problems, we avoid decimals. We cancel out and leave fractions. Fractions are good. Yes, they are. You learned to love fractions in Math 10. Oh, no, wait a minute. Oh, boy, that statement, which I will paraphrase. You learn to love fractions, then you forget about them, and you what? And then they're your worst enemy, she says. Okay, I'm really sorry I even said that on the broadcast, because fractions are your friends. I had to make this same statement to my statistics class yesterday morning when we were talking about probability, and we were getting 1 over 6 as our fraction. It was the chance of getting a die, of a pair of dice, to come up a certain number. Having a 5 come up, rolling a single die. 1 out of 6. They wanted to give me a decimal, and I said, no, fractions are your friends. Okay, you do have a valid answer when you change to the decimal, but it gets in your way. So you will not be doing very many decimals in an algebra class. Okay? So keep saying, I love fractions. Fractions are my friends. Take a fraction out for dinner tonight. Okay. Fractions are your friends. Okay. By the way, Chris, since you're going to be in Oklahoma, when is it going to be? This is the production. Okay.
March 20th to March 29th. Friday, typically Friday, Saturday, Sunday. The following week will be Wednesday
Okay.
at 10 a.m. and then Thursday, Friday, Saturday, Sunday.
We can't do a Wednesday at 10 a.m. because that's going to be our class.
Yes.
So you aren't going to be doing the camera that day. I can tell. You're going to be in the production. So again, March 20th is when it starts.
Yes, but you won't be able to get in because it is completely sold out.
Even with our connections in here,
Huh?
even with the connections in here with a performer, we couldn't get in because it's sold out?
I might be able to...
1 or 2, maybe.
Yeah.
Okay, so folks, we need to support Chris as he participates in Oklahoma. That's coming up. So we have a Bridge Bowl for football on the 28th. We have Oklahoma on the 20th. I mean, it's a busy month. March coming up. I want to do another problem. Okay, so I'm going to come back center. Well, I don't know about that. Let's look at number 49, and let's see how we would produce with that one. Okay. So the first question for Sandra. What does 21 over 35 reduce to as a fraction?
3 over.
Yes? 3 over? 3 over 5. Okay, 7 goes into 21, 7 goes into 35, so we have 3 over 5. Now this one I will write. Let's leave where it is for a moment, Chris, if you would. Boy, that one monitor up that I'm looking at has things with bloom on it, as it's called. But let me look at the one I have closer to me. And I have a 21, a to the 6th, and I have a b to the 1st, c to the 1st. They aren't written in the problem, as those of you watching can tell, particularly if you're watching the monitor, which is your only choice if you're doing this on 3C Media Solution Network. So much for the plug for that, Brian. Now, as we come back to this on the board, notice I put the ones. These are Isaac's ones. He's not here to appreciate that today. Noted his absence in so doing. A b to the 1st and c to the 1st. Sandra has already told me that I have a 3 over a 5. So let's take care of that immediately. Now, a to the 6th over a to the 5th, it's a to the 6 minus 5. You might have been able just to say a to the 1st immediately. The c to the 1st, I don't have anything I can do with the denominator, so I'm going to write c to the 1st, and I have Sandra scowling at me when I said a to the 1st. I'm getting there. I have a b to the 1st over b to the 2nd. Now I have a choice. What are my choices? I could say b to the minus 1. Or I could have said 3a to the 1st, c to the 1st, over 5b to the 1st, which is why I took it out of alphabetical order so that I could rewrite it here and still have the a and the c as they were the step above. But you would not see the answer that way. Most likely you would see it without the 1s as the exponents. Did I do something that I shouldn't have there? I'm seeing, again, scowls. Yes, Michael?
So when you have a positive exponent, the variable stays on the top?
When I have a positive exponent, the variable would stay on the top when possible. Have positive exponents. I'll rephrase it for you. So given choice, when possible, try to have positive exponents unless you're trying to avoid having anything in the denominator. Now, the reason for that, and I'll be with you in a minute, Robert. The reason for that is, and Chris, we need to slide over again. There we go. I'm trying to invoke this as a constant rule to follow. When you divide, subtract the exponents. When you multiply, add the exponents. So as I come back over to here, if I'm going to invoke the subtraction of exponents, then I'd have a b to the minus 1. But you need to understand that is equivalent to having 1 over b to the 1st. Again, new notation. You have the feeling that there should be some reason for it. The reason for it, Chris, sliding back over here, is if we use this rule, we need to understand what a negative exponent means. And this is the rule we use in algebra. And then you're expected, coming back over here, that, I feel like that optometrist again, lens 1, lens 2, that we will have positive exponents in your answer. That didn't sell. I'm getting a glare from Sandra still.
I'm just trying to figure something else out.
Okay, explain. You're trying to figure something else out. Share.
So whenever I cancel out, I could put basically the exponents anywhere I want because...
Whoa!
Well, not necessarily anywhere I want, but if I want to use a negative, I put it at the top. If I want to use a positive, put it at the bottom.
Okay, I follow you. You have choices. You can have a b to the minus 1 on the top or a b to the 1st at the bottom. Your choice. Unless you are told, as you would be in the computer program, to have it so you have positive exponents. Yes. So you have that choice. So if it's a negative up here, you can put it in the bottom with a positive. What is interesting, okay, you forced me into a corner. It's your fault. Let's say I have 1 over b to the minus 2. What's that the same as?
Oh, no.
Be with you in a moment.
No. 1 over...
1 over 1 over b to the 2nd, which is the reciprocal of the reciprocal, which is b to the 2nd. Now you commented about trying to just move things up and down. So if you have a b to the minus 2 in the denominator, it's the same as a b to the 2nd in the numerator. So I talk about sinking and floating. Now, Robert.
When a variable has an exponent like that, like you have b2 divided by b1, since the bottom one's bigger, can't you treat it like product of primes and cross cancel? Have like b and then b times b and then cross cancel?
Okay, what Robert's asking is if I don't want to get caught up in this silliness of exponents, couldn't I take this problem and rewrite it just as an example, one factor in particular? I have one b here, and this is b times b, so I can cancel that b with one of these b's and be left with a b in the denominator. You can always do that. But would you want to write out 6 a's and 5 a's and sit there and cancel out 5 of them as opposed to saying 6 minus 5?
Well, I mean, if it helps me.
No, if it helps you understand, I concur. And I was sort of pushing you in a corner. Because if I had a to the 600 and a to the 599, I don't think you'd want to write out 600a times a times a times a times a. You'd be here until lunch. Jessica.
So basically, in order to make a positive number, you would go with a number that's bigger and...
Okay, be careful. I understand what you're saying, but I'm going to clean it up.
Okay.
Isn't it basically saying that if you want to have a positive exponent, not a positive number, a positive exponent, then if the larger exponent is in the denominator, then just subtract this way. Yes, that'll work. But this one, the larger exponent, was in the numerator, so I subtracted the 6 minus 5.
And then you would keep it on top.
I'd leave it on the top.
And then you did all the above.
Yes, as we have here.
Okay, yes. Yeah.
Back to center. I have been asked by unpopular demand to do another one. I'm running out of good problems. Oh, that's dangerous when I start making them up, I'm told. 47. These are different than the ones you're going to see in the computer, so I don't have to worry about that. Okay, see if you can write the answer for me. Not yet. You have an answer yet? Not yet. Not yet is must be where the Russian came from. Was yet. Not yet. Yet. Okay, I hear several I got it, but I don't have it from everybody. I'm waiting. Okay, the pencils are about to stop. Okay, Sandra, your specialty. What does 9 over 36 become? 1 over 4. It's a beautiful start. Okay, now I'm going to back this off just this much, so you have t squared over t to the 5th. So what do you have left with t squared over t to the 5th? Erica. What is not the answer I was wanting? What do you have left with t to the 2nd over t to the 5th? T to the negative 3. Good. Or you could write it as t to the 3rd in the denominator. Good. Okay. Last part. I have a u. You don't see u. You see what? U to the 1st. That was, boy, a double U. Not meaning W as a letter, but double U's. Anyway, what do you have when you have u to the 1st over u to the 2nd? Michael.
U in the denominator.
U in the denominator. Do you realize how silly that sounds to say u in the denominator? U in the house, u in the kitchen, u in the denominator. Okay, so let me write that one in some space I have right here. This is going to be number 47, so that we can have that as 9 t to the 2nd, u to the 1st, over 36 t to the 5th, and I left the t out, u to the 2nd. So as we look at that on the board, Sandra's statement was we had the 9 over 36 became 1 over 4. She was right. Then, Erica said, if I have t to the 2nd over t to the 5th, I could just subtract the exponents and get t to the minus 3. So, I could rewrite this then, and I'm not sure where I'm going to try that. I'll try coming just down here. So I have 1, and then I have a t to the minus 3, and then we had a u to the minus 1 over a 4. Now, I sort of like that because I ran out of space down here. So that gave me an option of putting everything on top. If you really wanted to and had fun with this problem, 4 is 2 squared. So I could have written 2 to the minus 2, t to the minus 3, u to the minus 1.
What?
Yes.
How do we get it?
You'll get it. This is looking bad when I have the minus
Is that
1.
over 1?
Yeah, technically that's all over 1.
Okay, now I got it.
I don't think I like that. I'd like
I give you a gift and you say, I don't like it. There's a 4 down here, which is really 2 squared. Since it's in the denominator as 2 squared, I could have written it as 2 to the minus 2 on the top. It's just an option. Why would I want to do that? I wanted everything on top. It's a mountain to climb. It was fun. You're glaring. You glare at my board work a lot sometimes. Michael.
Is it going to matter if we have the variables on the top of the fraction or on the bottom of the
Ah, nice intuition there. Does it matter if I have the variables on the top or the bottom? At the moment, the answer is no. In the future, yes, it makes a difference because technically these variables are on the bottom because I would have had, as we said, t to the third in the denominator, u to the first in the denominator, and I'm worried about denominators when they're 0. Let that sink in. If a denominator is 0, I am in trouble. So if t is 0, I am in trouble. If u is 0, I am in trouble. So I have to have an implied restriction. It says any value for t and u you want except 0. Okay, I'm going to throw 2 more phrases in here that you'll want to remember for the next 20 years. Okay? For those of you who... Okay, not disappearing ink. Okay, and pen. This is in concrete. The values that you can substitute for a variable are called the domain. The values, the set of values that you can substitute would be considered the domain. Now, the domain is the set of real numbers for just about everything we're doing. Now, we restricted, notice the phrase, we restricted our domain at the beginning so we could only have whole numbers. We have lifted the restriction and replaced it now with a new one. Integers. We've lifted that restriction, and now we're allowing fractions called rational numbers. And eventually, we lift that restriction and say it can be rational or irrational, hence real, a real number. Any decimal you want, repeating, terminating, or non-repeating, non-terminating, like the square root of 2 and pi, which was 3.14159 with an awful lot of garbage to go. Doesn't repeat, doesn't end. So, domain, the set of numbers used for the variable. If I have to restrict that set so that t cannot equal 0, u cannot equal 0, we call it a restricted domain. That's the phrase, restricted domain. Sandra.
Can you repeat that, just that last bit about the restricted domain?
If I have values that I cannot allow, and the values here were t at 0 and u at 0, because they would have been in the denominator, and I cannot divide by 0. So I have to restrict those values for my variable. I can't have t equal 0. I cannot have u equal 0. That means we will consider that a restricted domain. Bomaro. We could probably do them all day long. However, I'm going to have to let go of this and answer another question that Tabitha had from 4-5 so that we can take a quiz, and I have reasonable confidence you will do well in that quiz. We will come back to this on Monday. Before I leave this, Robert.
Just to be certain, the answer is a fraction.
This is a fraction. It's understood to be a fraction. Of course, 3 is a fraction. 5 is a fraction. It can always be written as 5 over 1, 3 over 1. So any whole number, any integer can be written as a rational number. The negative exponents do not make it anything different. And just one more comment, and this is serious. If t and u are replaced with positive values, my answer will be positive. The negative exponent in no way makes my number negative. Negative exponents do not influence the sign of the number. They just tell you whether that variable is really somewhere else. This says, it looks like it's on the top, it's really on the bottom. Okay, I'm coming back center. There are times when you're doing algebra that you get a real feeling that people aren't very happy as they glare at the problems and glare at you. And which problem again was it? 35. Okay, so this is on section 4.5, and it's problem 35. Now, I thought I was in the right spot. I'm looking at a review exercise. There's my difficulty. Okay, we've got some money. Well, that's probably a bad thing to say in this economy, to say we have money. We have a problem about money that we don't have. Now, it would be nice if our economic problems could be solved like algebra problems. Wouldn't that be neat? Let's go to the document, Cam. This person has some bills, and these are the kind of bills you like. $5 bills, $10 bills in the wallet. Now, you just take the money out and count it, but nonetheless, it makes a neat problem. You've got $125 total. He has 19 bills total. Okay, so that's an important phrase that is critical to this problem. So what I'm going to ask, as you think of this problem, read it for a moment, and then look up from the book and see if in your head you can repeat what's there, even though you're not reading it. So again, you read it, look up into the air, and see if you can restate the problem in your head. Okay. What's my first thing we do is we go to the sideboard. Nope. Let x. Yes. You understand let x is going to be your first step? I hope. It's what I'm looking for. Let x equal what? The number of either 5s or 10s. Doesn't matter. What's your choice, Sandra, since you said let x?
10.
The number of 10s. So x does not equal 10. If you said let x equal 10, nothing happens good. It's what? The number of $10 bills. Now, the minute Sandra makes that commitment, and you could have said instead the number of $5 bills, it is an arbitrary choice. How many $5 bills do I have? Yes, I do. Close. Let me ask you this. If I tell you I have two numbers and one of them is 7 and the total is 19, how do you find the other?
Oh, isn't it 5?
Two numbers add together to give 19. One of them is 7. What must the other number be? 19 minus 7, correct? So if x is the number of $10 bills and I have 19 total, how about 19 minus x is the number of $5 bills? And Tabitha, that is the key to the problem. And that we can get around if we allow two variables. Now, we are in algebra at some point going to say, Well, let's let x be the number of tens, and 5 we'll use for y. And you get an equation very quickly. X plus y is 19. Michael?
No.
Okay, you're okay. Now, I know that I have $125 total, correct? Would you want to carry around 19 separate bills in your wallet for $125?
No.
Probably not, but this person did. And I'm not sure why a problem like this, unless you've forgotten how many bills you had of each. What is the value for each of these X $10 bills? It's $10, correct? So the total value for that is 10X. So I have X $10 bills. So if I had 5 tens, it'd be 50. 4 tens would be 40. 3 tens would be 30, right? Then I'm going to have what? No. These are my $5 bills, correct? If I have that many,
Oh, X plus C.
5 times
Oh, yeah.
19 minus X. If I have this many, see, I want to go this way and face sort of Tabitha and the camera simultaneously, which means I'm going like this. But if I look at what I had for the 19 minus X, each one of those is a $5 bill. So if I have 12, I multiply 12 times 5. If I had 8, I multiply 8 times 5. Well, I have 19 minus X, $5 bills, so I multiply that by 5 to find the value. And all total, this has to be $125. And that's how I get my equation. So this is a critical step up here. This is your next critical step. And that gets you major credit. Now, from then I have to do what? Solve. And I would use the distributive property. So I have 10x. This, by the way, of all the silly mistakes you make in an algebra problem where the hard part's done, this is where silly mistakes get done. Now, I do 5 times 19 in my head by saying 5 times 20 is 100 minus 5 is 95. And then minus 5x, and I sort of like that because 10x minus 5x is 5x, and that's 125. So this is 5x. Now, whether you take this next step or skip it and go to the next one I'm going to write, which is 5x equals what? 30. You might want to just skip this one. I don't object to that, but whatever you skip, be careful, because just make sure you didn't make a silly mistake in the process. X then is what? 6. Now, am I done at that point?
No.
Technically, no. This is a solution to the equation, but I would guess that you were supposed to, in this problem, tell me, how many 5s and $10 bills do you have? So you have 6 tens, so I have 6 of these, and I'm going to have 13 of these. How do you check your problem? Yeah, plug in the values, or you just say, well, 6 tens, that'd be $60, correct? And 5 times 13 is $65. And if I add those two together, do I get $125? Yes. And so you have to be careful in this way. Be very cautious now. If I just substitute into here, I might have a correct solution for my equation. But what might have happened? I might have written the wrong equation for the information. So what you're going to be admonished to do is substitute your answer back into the original problem and see if it makes sense to you. Does this sequence or this combination of bills work? Yes, it does. But if I had the wrong equation, I could have a correct solution for the equation, but not for the problem. There's a subtlety there. Okay? Tabitha, are you happy with that solution?
What if you did work with what X equals? What if you did $5?
If you said X was $5 bills, then you would have had an answer of 13 when you finished. And then You take 19 minus 13, and you'd had 6 $5 bills. No, you would have had, 6 $5 bills. It just reversed it. But would you still have the same combination of 6 10s and 13 5s? Yes. That wouldn't change. It's just the expression would look differently, because here you would have had 5 for this and 10 for this, but you're still going to end up with the same answer at the end. We got it? What about tables? Tables are nice. I have them in the kitchen, and I study at a table. And the question is, do I have to do a table? Let's come back to the document cam for a moment. The question is, what do I do with that table? Well, you can use it if you want, and so how would you use it? I would say the categories are, and let me slide that over now, the categories of problem, or category would be 5s and 10s. So I have $5 bills, $10 bills. I don't know if I want to say it that way. That's sort of strange, isn't it? Category, value, and number. The value is a 5 and a 10. The number is an X and a 19 minus X. And then I have what? The value, or the amount being, and this is where you'd have like a 10X and the 15 times 19 minus X that we had in the sideboard. How would you do this? Just write out $10 bills, T-E-N, and $5 bills for categories? 10s and 5s, which has a value of 10 and a value of 5, which seems redundant. So that classification of categories may be a little bit unnecessary. So again, let's see what I can write down here. People keep leaving me various tools up here, none of which I can use. I want a pencil that you got one I could use there for a minute, Michael? Thank you. And this has number 5 lead in. 0.5? Good, then I may not break it. Okay, so this is a value of 10 and a value of 5 if I chose that. And since I'm letting X be the number of $10 bills, I have X here. And here I have 19 minus X. Then my amount, this means what is it worth? And suddenly, that's interesting, the glare. Okay, if I move that over, now you can see the 10. And then that's disappearing like a ghost. But I'm going to have a 10X here for the amount. And here I have a 5 times a 19 minus X. And then this total, I could come here with this like out here and say that's 125. And that is the sickest looking numbers I've written in a long time. Your pen and I do, thank you, Michael. It's not your pencil, it's my writing. But does that answer your question, Tabitha, how I would do it? Now, let's come back off there for a moment, Chris. Are you obligated to set up a table? Not in terms of solving the problem. Now, I don't know to what extent on the computerized homework, if you are expected to set up a table. Has any of you had to do that in the... Okay, so in a way, I'm painting you into a corner I didn't intend by saying you're going to have to come up with these tables on the computer. From an educational perspective, forcing you to do tables is a nice way, I guess, of giving you help. But as a student, I would find myself being a bit rebellious and saying, hey, I don't need a table, so I don't want to do the table. And having to do the table would be irksome to me. So my apologies if very many of those are asking you to set up the table. Bear with it briefly. I do not demand, expect, or otherwise want a table on a quiz or a test. So tolerate the tables only as long as you need. So if you like eating on the floor, get rid of the table. Michael.
I came across the problem when I was doing with the triangle, and I wasn't aware that all the angles on the triangle are 180.
Okay. This is something that I glossed over briefly. And it was a statement I remember making verbally, but I certainly didn't hit it home hard enough that it would be retained. Michael's question has to do with the sums of the angles in a triangle. And that being that there are 180 degrees for the three angles of a triangle, just like there is a total of 180 degrees for a straight angle. And so you had to know that in a triangle, you would have had a total of 180. And I made it in passing when we were talking about the straight angle, how all these would have to be 180, just like in a triangle, which has 180, but that parenthetical statement certainly doesn't qualify as a heads up, remember this. Sandra.
Now, is that for all triangles?
Yes, all triangles. Yeah, that's neat. I like your response. That's the kind of response I want in mathematics. Wow, that's all right. The angles in a triangle add up to 180.
That's good to know, because when you're doing a problem, you already know the equal sign.
Yes, is 180. Yes, isn't that marvelous?
I like that.
Me too. I love the enthusiasm. Okay, we have time for one problem, maybe. Which one is it?
It was the triangle problem.
The triangle problem. I guess I'm probably going to go to the side. Is it one of them from here, or?
No, it was on the computer.
Okay, but I need to find a triangle in here that's I can show people and say, aha, a triangle. Okay, when you need a triangle, you can't find a triangle. Okay, this is ridiculous. Okay, up here I have a triangle. There we go. This one happens to have 60, but let's go to the document cam. Now you tell me about your triangle.
Yeah, angle B is 4 times angle A.
Okay, so I have a triangle with 3 angles. Okay, so scaling, right? No sides necessarily equal, and this is, boy, I don't know if I've managed it or not. So I have A, B, and C. Just for your viewing pleasure as we come to the board, some new information. Hold on, hold on, before we go. That is not a right angle. Okay, it's looking too much like a right angle. It is more than 90 degrees, called an obtuse angle. But the side opposite, that large A used for the angle, is little a. The side opposite big angle C is little c. And the side opposite big angle B is little b, just in passing. Now you have angles A, B, and C, and we have capital letters for those angles. Continue.
Angle C is 90 degrees less 5 times angle A.
Is that what I heard? Now notice, I didn't put the angle, I put the measure of the angle. That's a little bit picky, but it's good geometry. So the measure of angle C is 90 degrees less than 5 times the measure of angle A. So what would be maybe that I want for X?
No, 9.
Oh, 9 degrees. Okay, well that's just a 0. They don't mean anything, right? Big difference, right? Okay, now with this, I would probably let X be the measure of angle A. So that means I can say now that the measure of angle C is 5x minus 9. Okay, what else? Just restate it.
Well, and then it wants you to find the measurement. It wants you to find the angles for A, B, and C.
But I have to have some other information, don't I?
Well, I didn't write it down.
Oh, okay. So there would be some more information about angle maybe B in terms of A, and then those 3 angles have to add up for 180, and we'd be in business.
Angle B is 4 times angle A.
Oh, so the measurement of angle B is 4 times the measurement of angle A, so I have this is 4x. So if I take all that together, x plus 4x plus 5x minus 9 must be the 180. The sum of the 3 angles being 180. So I have x, 4x, 5x. That's 10x, which is very nice. I don't like this at all. Have I done something in error for what you've written? Yeah, because this comes out at, this is going to be 10x is equal to 189. And x is going to be 18.9 degrees, and we've been pretty much taking the position that we're going to have integers. So this is a case where, in essence, we have a problem that was probably poorly constructed. Okay, with that, I'm supposed to be done with the broadcast at 11 o'clock on the dot, and we're down to 2 minutes and 5 seconds. And were we not? That's 10:57. Okay, so we're going to bring closure to this momentarily on Monday. So again, those of you who are watching and wanting to know where we're headed, on Monday we're going to continue with 5.2 and see if that works a little bit. I do not have the problem selected for 5.2 and 5.3. I'm going to do that this weekend. So pay attention to Course Compass. My math lab, I'll be selecting problems this afternoon, is my hope, and have that set up for you. So as we go back to